So this is week 5. Okay. So I'm going to talk a bit about biplots, and after that we will say something about feature selection, right? Feature selection on filter methods. Okay, the more advanced feature selection methods we will cover after we come back from the break, right? Okay. So the biplot, okay, so if you remember, right, so the biplot is something like this. After you, in R, you can, so you have, you can create an object PCA, which you can run using printcom, right? So this is for R mode, right? PCA, printcom of your data sets, right? And then, so after that, you can just invoke biplot of the PCA object, right? So then the R will produce, you can actually select the axis that you want to look at by controlling. There's actually an argument here. If you don't put any arguments here, it will just produce the first two principal components, right? I think there's some, later we'll look at that. You can actually change the principal components that you want to look at, right? Maybe it's 1, 3, maybe 1, 4, or 2, 3. Okay, you can actually change that. By default, it will show the first two. Okay, so let's look at the default first, right? So the default will be something like this, and you might actually get some. So you might, let's say, for example, the plot looks like this, right? Okay, and then you are going to see arrows on the plot. Okay, so arrows might be, you might use a different arrow. Okay, might see like you might get some arrows that are like this, some arrows that are like this, then there are some arrows maybe let's erase this. Okay, maybe another arrow that's like this. Okay, maybe it's an arrow that's like this. Okay. Okay, so each of these may actually represent a particular variable, right? Let's say this is variable 1, this is variable 2, this is variable 3, and this is variable 4. Okay, so what happens is that it actually scales. What is done is actually this plot, right? The relative positions of the data points in the principal component space is unchanged. All right, but it has been scaled, right? In such a way that here, over here, you see that there's for this particular variable, this will be its the length here. This will be its x component, its component along principal component 1, right? So this value here will be its loading on PC1. Okay. Example, your PC1 may be something like this, 0.5 times x1. So in this case, then maybe then the other one is plus 0.2 x2 plus 0.00 something 1 x3, then minus 0.5 x4. Okay, so this 0.5 is actually the length here. Okay, so this vector has an x and y component, right? So the 0.5 will be here, and then for x2 you can see that the x component is until here only, right? Okay, so corresponding to 0.2. For x3 it's actually very small, right? So So it's like your X3 is something like this. It's like perpendicular. It's actually along your PC2. And minus 0.5, right? It's on the negative side. So you can see that actually the minus 0.5 represents the length here, okay? And then for your PC2, you can have, so PC2, this should correspond to something like 0.1x1. Your PC2, okay, here is negative, right? So it will be negative 0. Maybe say 3x2. Over here, this will be positive 0.5x3. And then over here is negative, right? Negative 0.1x4. So you can see that over here, this length, this height here is 0.1. This height here is so the value here, so this value here is minus 0.3, okay? So 0.5 up to here, and minus 0.1 over here, okay? So this will be minus 0.1, okay? So in fact, it scales the space in such a way that when you put the arrows there, right, on the it scales the space in such a way that by just looking at the coordinates of the x and y, the x component, right? So on the PC1 and PC2, you can actually put a vector, okay? A vector where the x component is actually this loading and the y component is this loading, okay? So then it allows you to put the vectors on this space, right? To help with the interpretation, right? Therefore, you see that from this biplot, you can understand why certain data points they cluster in certain positions. Like for example, the data points here, right? They are definitely positioned here because they are relatively strong with respect to this variable x1, okay? And they are also here because they are relatively weak with respect to x4. You see that they are pulling in different directions. So they are here because they are strong in x1 and they are weak in x4, right? Similarly, for this group of data points, they are strong in x2, okay? But they're strong in x2, but possibly weak in x3, right? Because x3 is pulling in the opposite direction, right? And so on and so forth, okay? So then you have this group, right? So this group is probably somewhere in between. They are probably kind of like strong in x3 and x4, roughly. And they are weak in x1 and x2 because they're pulling in different directions, right? So the biplot will allow you to interpret the results quite intuitively if you know how to read the vectors, okay? So far, is it okay? How the vectors are actually related to the loadings in the principal components? Is it okay? Or do you need more clarification?
It's okay.
Okay.
Right. Okay. So far, so good, right? Yeah, Amy, the attendance later I will during break time I will edit. Okay. So just ignore that for the time being. Okay. So let me clear this. All right. Okay, so let's look at the other situation. Okay, so let's look at the other things that we can get from a biplot. Now, okay, let's say you have some arrow like this. There's an arrow here. Maybe one arrow here. Okay, right. So you can also so the length of the arrow, right? You can see that some arrows are long and some are short. So the length themselves, because the length is influenced by the X and Y components, right? If your X component is strong but your Y component is not so strong, then you'll see that the line will pull kind of like with a smaller angle, right? Along the X-axis. Okay. So for arrows that are very short like this, you know that this variable, right, is actually not important in influencing this principal components, right? Because it's a loading on C1, PC1, and PC2 is actually small, right? That's why the arrow is actually short. Okay, and for this arrow here, maybe I should just label them X1, X2, X3, X4, X5. Okay. So like for something like X2, right? X2 is very strong on principal component 1, but absolutely it does not affect on principal component 2 because its Y component is almost 0. Yeah. So you can actually tell which variable affects the principal components by just looking at the length of the arrow. Okay. Now, then the other thing to look at is you can actually look at correlations. Yeah, correlations between pairs of variables. Okay, and the correlations. Yeah, this is your usual Pearson correlation. Okay, and of course this is presupposing that your variables here, they are numeric. All right. It will just basically calculate a Pearson correlation. I mean, you can, from your data matrix, right? Of course, these are your samples, right? It will straight away just calculate a Pearson correlation between the two variables. Okay. Please note that this Pearson correlation is a global. It's a global correlation. Okay. So it does not take your label into account. Yeah. Okay. So it should be considered as something like a rough, just giving you some rough idea about the relatedness of these two variables. Okay. So you can get the correlation by looking at the angle. For example, if you want to find the correlation between variable 1 and 2, of course, this is the sample correlation, yeah, because you're dealing with samples. It's actually equal to the cosine of the angle between them. So this angle here, the angle between these two vectors, let's say I label it theta 1, 2, yeah. So you take the cosine of the angle, that will be equal to the correlation, right? The Pearson correlation. So obviously, if the theta is small, right, then your cosine of theta will be high, will be close to 1. Okay. If you remember from high school trigonometry, the cosine of 0 is 1, right? And cosine of pi over 2 is 0. And the cosine of values, let's say like in something like 150 degrees is actually negative is a negative of cosine 30 degrees, right? So that will be what's that? That would be something like minus square root of 3 over 2. You don't have to panic with cosine. You can actually basically just calculate that from R, okay? But it's nice to know, recall these basic properties, okay? So that's why if you see, if two vectors are very close to each other and they're almost parallel, like something like this. Let's say I draw another vector that's almost parallel to this vector, then you know that these two variables, right, are strongly correlated because strongly and positively correlated, yeah, because the angle here is very small, right? So the cosine will be close to 1, okay? On the other hand, if you look at x1 and x3, right, their angle is almost 90 degrees, okay? A cosine of 90 degrees, which is pi over 2, is almost 0, okay? It's, well, exactly 0 if you have pi over 2, okay? So that means your variable x1 and x3, they are uncorrelated, right? Just from the biplot, you can actually tell, okay? And if they form, so if they form an angle that exceeds 90 degrees, right, something like this. Okay, so this will be a, maybe this is cosine 120 degrees. So what will this be? This will be cosine 60 degrees minus, okay. This will be minus 1 over 2. Okay. So that will be a negative correlation. All right. And in fact, if it's pulling in the completely opposite direction, right? Like let's say I have something like this. Let's say I have one that's pulling totally opposite of x2, yeah? Let's say I have x6, right? So in this case, your x6 and x2, okay, they are pulling in different directions, right? So this angle here is 180 degrees, that's pi. So cos pi is equal to -1, okay? Which means your variable x2 and x6 are negatively correlated, okay? So one is going up, the other is going down, right? Negative correlation on the other direction, okay? So in fact, the biplot is actually a very useful, it's a very information-rich diagram if you know how to read the vectors, right? Otherwise, they would just appear to be very strange things that people put on a plot, and you are not aware of the what you can actually interpret from this kind of diagrams. Okay. Right, so that makes the biplot a very useful graphical method to understand your data, okay, in low dimensional space. All right. And in fact, in the biplot, there's also one more thing. In the biplot, you have, so this so of course in your biplot you have data points, right? This is in the biplot space. Okay. The biplot space actually it will tell you. So in the biplot space, the distance between the two data points here, they are, you can have distances like this, right? So the distances in a biplot, they are approximately equal to the Euclidean distance between the samples. Okay, so you take two samples here, you find their, so the distance here, right, in the biplot space is approximately equal to their Euclidean distance. Right? Of course, you can calculate their Euclidean distance separately. Okay, but it's nice that you can actually approximately see them on the plot, right? Which is nice because then points that are close together, they are close in the Euclidean sense, right? Easy to interpret, right? Because Euclidean distance is the usual distance that we are talking about on a flat space. Okay. So this is also one more thing. So the distance in the biplot actually is meaningful in the Euclidean sense. So now let's look at some examples. Let's go to maybe the iris data set. All right, let's look at the iris data set. So can you see my console? Can you see my R console?
No. Yes.
Can?
Yes.
So let's do a PCA for the iris data set, right? So, okay, let's look at the iris data set first. This is a classical multivariate data set, right, of flowers. So the fifth column is the label column, right, for the species of the flower. So we have already looked at this data set before, right, when we were looking at variable construction, okay? Now let's look at do a PCA directly. So PCA using print.com of iris. Now you got to remove the last column, right? So that will be n core is the number of column of iris. Okay, you can either do minus n core of iris, or you can count the number of columns. Then the fifth column, right? 1, 2, 3, 4, 5. The fifth column is the column for species, and you replace it with a number. That is also okay, right? But this is more general if you put minus n core iris, because it's going to delete the last column, right? Then you don't, because especially if your table is very large, right? Sometimes you're very lazy to count the number of columns. Okay, so you can do this. By the way, you can know the number of columns by checking the dimension of iris, right? So the first value is the number of rows, the second value is the number of columns. Okay. So you got your PCA done already, and you can directly put biplots PCA. Right. Okay, so can you see? Can you? You probably can't. Let me show you the diagram. Can you see the diagram?
No diagram.
No diagram. Share. Share. Okay, can you see it?
Yes.
Yes.
Okay. So over here you can see that your petal width, right, is going in the same direction. It's actually parallel to petal width and petal length. They are like parallel, right? So their angle is almost 0. So their correlation, you would expect it to be almost 1. Okay, and you see that the sepal width is kind of like pulling away from petal width or petal length. The angle is roughly obtuse angle, right? So more than 90 degrees. So you would expect that to be maybe slightly negatively correlated. Okay. So we can check that, yeah. So let's try to check. We can go back to the console. So can you see the console?
Yes.
So so we look at the correlation of iris sepal length, iris. Sorry, that was just now. It was a petal length, right? Petal length and petal width. Okay. So you, as expected, you see that the correlation is 0.96, yeah, which agrees with our intuition, right? Just now we look at the angle is extremely small. Then we look at the correlation between sepal width and one of these petal lengths, all right? So we change this to sepal. Okay, we can see that the correlation is negative, right? As kind of like expected. Okay. In fact, yeah, this is minus 0.42 something. Okay. So if you look at what else, okay, let's go back to the diagram. Can you see the diagram?
Yes.
Okay. Do you notice that the sepal width forms like approximately the vector of sepal width is approximately perpendicular to sepal length? The two arrows, they form like
Yes.
right? So we would expect their correlation to be sample correlation to be close to 0. Okay, so let's check that in the data set. Okay, let's try. Try a correlation. Can you see my
Yes.
console? Okay, sepal width and sepal length. Okay, let's change this. All right. So you can see that the correlation is actually close to. It's not exactly 0, but it's close to 0. Yeah. All right. Just the angle is also not exactly 90 degrees, right? But something approximately. All right. So again, it gives you some good idea, yeah, about the amount of correlation between the variables based on the vectors in the biplot. Okay. So, do you have other questions for this part regarding biplot?
No.
Okay. So later you can actually use these techniques in the assignment that I will talk about later. Yeah. So I've got that for assignment 1 for everyone. Okay. So I think we are okay already with PCA, right? So using PCA to the basic theory and also how to apply it and interpret the results. All right. So now I want to talk about the idea of feature selection. Right? Okay, so feature selection is one way to do variable selection.
Doctor,
Sorry.
Doctor,
Yeah.
there's someone asking question in chat.
Oh, okay. Thanks. If using Ching, if using PC2 and PC3, the angle will be the same for particular pair of variable. I think so. Yeah, that's a good question. Actually, it's correct. Yeah. Right. So if you have PC2 and PC3, again, it is basically reflecting the vectors, right? They actually reflect the positions, right, of the loadings. Actually, why don't we look at this? Why don't we go back and verify this? Yeah, this is actually a very good question. Let's go back to the console. We verify it with our own eyes. Yeah. Okay. I have to push it like this. Somehow the clear screen seems to be kind of like broken in the laptop. So okay, never mind. Can you see my console?
Yes.
Maybe let me try by plot PCA. I think, okay, so I don't remember how to do the other thing. So, but I can use a question mark by plot and check the documentation. So let me see, by plot. Okay, so basically I just need to supply it with a vector. Okay, so basically by plot PCA, if I choose C1, if I give it a vector 1, 3, it will plot 1, 3 for me. Okay, let me show it. New share. Oops. You share. Can you see the plot?
Yes.
Okay. The plot is okay. So this is the principal component plot for. So this is a biplot for principal component 1 and 3. Okay. More formally, you would say that it's a scatter plot of. Well, it's a biplot of component 3 against component 1. We usually mention the one on the y-axis first, right? But anyway, so you can see the axes are positioned. Sorry, the vectors are positioned like this, right? So again, that roughly tells you, like, for example, you look at the angles, right? So your petal length, okay, your petal length and your petal width, right? The angle is actually small. Okay, so you can so you expect their correlation to be large, right? But again, I think this in this representation, it may not be so. It may not. Just now you saw that the two vectors, right? They are actually almost parallel, right? But over here, you see that the two vectors actually have some gap between them, right? Petal width and petal length. Okay, so I think I would say that the approximation is actually rougher. Okay, you can still use that idea of looking at the cosine of the angle, but then you have to treat it more as an approximation when you look at other kinds of spaces, right? PC1 and PC3, for example. I think the correlation is the interpretation of the cosine of the angle is strongest when you look at the first two principal components. Okay, but more or less you could still get the rough idea about the correlation between the variables by looking at the direction of the two vectors. Okay, like for example, your sepal width and sepal length, the angle is still obtuse, right? More than 90 degrees, so the correlation is negative, right? So you are basically getting approximately similar kinds of information, although the one from PC1 and 2 would be maybe more accurate, I would say. Okay. So that's actually a good question. Yeah. Okay. So are there any more questions about the biplot? Is it dependent on the percentage of variation that is explained by the principal component? I think so. Yeah. So because your first two principal components, they are the ones that explain the most amount of variation, right? So So you also have to understand that you are kind of like projecting your data from high dimensional space to a low dimensional space, right? So of course, the correlation that you calculated on the raw data is basically just 2-dimension, right? Because you're looking at pairwise, okay? But your principal component space is actually slightly more complicated, even though it's in 2-dimension, but it's slightly more complicated than your original pair. But it's good enough. It's usually good enough to approximate the correlation that you calculate based on the columns. Okay. Are there any more questions? Okay. So if there are no more questions, let me move to the topic of feature selection. Yeah. Okay. We have feature selection. Feature selection, or you could also say it's called variable selection. Okay. Now, so your data set may actually, so this is your data set, right? These are your variables, okay? And so on, right? You may actually have p variables, right? And these are your these are your samples, okay? Okay, so what happens is that some of this, it turns out that not all of these variables that you have in your original data set should be used, because so it's actually not true that some people may think that more variables equals more information. This is not strictly true. Okay, it's not strictly true. Just like it is not strictly true that the more people you put onto a job, the better it will become. Maybe up to an extent, right? And after that, it may not actually have any effect, and in fact, it may actually cause a kind of degeneration. Okay, so you have to use just the right amount of people for the job, and so it's the same with your analysis of this kind of data sets, right? You have to use just the right amount of variables, okay, for the downstream analysis. All right, so for this, you have to decide which variables should go in to the downstream analysis and which you should leave out. Okay. So, for example, the classic example would be you have maybe you have a class label here. Right? So how do we do this selection? So I'm going to start with a simple example. So you have a class label. Let's say these are all zeros. The others are all 1. Right. So let me erase this. So ideally, you would want to find out, you want to use those variables where there is a strong, where the variables are maybe discriminative for the class label, right? Because ultimately you want to find variables that allow you to explain, right, where the variation in the particular variable explains the variation in class label. Okay, what does that mean? Okay, so 0 and 1 is actually a variation, right? It's a variation in class label, right? Variation is actually just a formal word for difference, right? That's variation. Okay, so if these values are actually high, I just shade them like dark, right? And these values are actually low, right? So there's a contrast, right? There's a contrast of between the high values and the low values, and this contrast actually is actually associated with the zeros, and these are with the ones, right? So this means that this variable actually is pretty good, because if I see a high value for this variable, then it's associated with 0. If I see a low value, it's associated with another class label. Okay, so these are the variables. This variable is actually good, right? If you look at the other variable, they are more or less the same value. Okay, so for variable 1, then it's questionable. Okay, because whether your so the values are more or less the same, right? So it cannot help you distinguish whether it's 0 or 1, right? So this variable is actually a candidate that you should consider getting rid of, right? Of course, in most practical problems, this kind of variables may not be easy to get. So it will vary from problem to problem. In some problems, if you get some variables that have some kind of modest kind of variation, it's already pretty good. Okay, this kind of pattern of variation is very strong, all right, and you're unlikely to actually get it in a lot of real data sets. What you might potentially get is maybe something like this. A bit of it has just slightly more kind of information, slightly more kind of variation, right? It's not like in the first case x1, but it's better, right? The hope is that if you get enough of these variables, if you can find enough of these variables where there is at least some kind of association, right, between the values in that variable with the class label, you have enough of them, it may be enough for you to make a distinction, right, between the class labels. Okay, so that's the idea. And your hope is to get rid of all the noisy variables, right? So like some variables that are very high in across all the values. So this is also not useful because there's no variation, you see. So whether it's 0 or 1, same, right? They are all highly high values. Okay, so that kind of variables is not useful. Okay. So so what can we do? What sort of methods do we have to actually detect such things? So we'll have to look at let me clear this. We have to look at some examples. So the tool that we use will actually depend on the type of the data. So if you have, let's look at the data. So let's say your data, let's say it's a continuous type. Okay, so then the natural candidate will be a t-test. If you have if your class label is binary, okay, that means you have only 2 types, right? So the t-test will be okay. When you do the t-test, basically you are using the test statistic. You are not actually you are actually not doing a hypothesis test, right? You are basically just calculating the value of the test statistic and using the test statistics, the t statistic to rank rank the variables, right? So, and usually how we do this is that we will look at the absolute value of the test statistic, because your t statistic can go to negative or positive, right? Depending on it. Basically, it's just saying the mean is which one is larger, the first one in the first group or the second group. Okay, so the negative does not actually have much meaning. It's just a direction thing. Okay, so we can take the absolute value. So basically, so you can basically calculate very quickly. So these are your variables. These are your class labels, 0, 1. Okay. So for each column, right, you could compute a test statistic, right, a t. You can take absolute. Okay. So suppose you get different values. Let's say this is 25. This is 0.5. This might, so this may be 2.1. This may be 14. Okay. Right. So after that, you can rearrange them. Right. You can actually order them, and then you can actually plot them on. So this will be the variable. This will be your absolute of t. Right. So you might actually see something like this, and then it may jump. Okay. So the way we actually check this is that the graph will be more useful if you actually have a lot of variables. Yeah. Otherwise, you could basically just check the vector here, right, and then just from there determine which ones are large, which ones are small. So the ones that are small are actually not useful. Okay, like for example, these are relatively small, right? They are not useful. The ones that are relatively large are useful. Okay, so for example, these ones are good. Okay, so usually one very commonly used method is, once you see this graph, right, you find the point, right? Because sometimes often the question is how many do you want to take. So for this, you basically there's no formula for that. It depends on the data miner. But a general rule of thumb is that you can use this diagram to help you, right? So the moment you see that there's a jump, right, and sometimes very often you may get a situation like this. So if there's a jump that occurs between this variable and here, right, so you will take the whole set here. Okay. So these ones, you consider them as low value variables, because their test statistic value is not big enough. Okay. So once you settle on this set of variables, then you basically eliminate these guys, right? You eliminate these guys and you use the reduced the variables, the set of data with the reduced variables as the next step to do your work, whatever work. Okay. So this is the case when you have binary labels. Yeah. How about when you have multiple class, multi-class? Like you have you have more than 2 classes. Yeah. This could happen very often.
Chi-square?
So you have, sorry?
Is it chi-square?
No, okay. So it would actually, what test you use actually depends on the data type. So we are still talking about continuous type. Yeah. Numeric. It's a numeric data. Okay. Yeah. So you have to use an extension of your t statistic, which is ANOVA. Analysis of variance. Analysis of variance is a it generalizes your t-test. ANOVA can do it simultaneously for several, more than two. Of course, you can use ANOVA for binary as well, but that would be equivalent to a t-test, right? So generally people will use ANOVA. You calculate so ANOVA, it will report the F statistic. So you use the F statistic in ANOVA, right? Can I check with the students here, how many of you are not familiar with ANOVA? You can just reply in the chat box. I just have a survey only. I would say if you don't work with data often, right? You are unlikely to be familiar with ANOVA. Like if in your training you have not dealt too much with data, then quite possibly you may not be familiar. It's okay. If you're not familiar, we just learn in the course, right? Because I just want to know. Otherwise, I might think that you actually are okay with it. Then I will not go too much into ANOVA. Or at least I will maybe briefly give you a conceptual understanding of ANOVA, what it is. So others are okay. ANOVA. Okay, seen before. All right. Well, at least you've seen it before. It's pretty okay. All right. Okay, Ziyun, you said should be okay. So can you just explain ANOVA in words to me? Basically, what is the F statistic calculating? It's okay, just try. Okay. Right. Okay. So I think, yeah. So maybe later I maybe just give a brief example, brief explanation of ANOVA. Actually, ANOVA is a very interesting. It's a very interesting way to understand data. The way it actually partitions the variation in the data to different sources of variation. It is a very interesting way of thinking about what are the sources of variation in your data. The sources of variation can come from between the groups. It can come from within the groups. And then, so that means it can be explained by the variation between the group. It can be explained by the variation within the group. And also there's a part that is not explained by the variation in either of these two components, right? So that will be some unknown variation. I mean like some unknown sources of variation. So because of this, right, it can actually give you some kind of idea what is the amount of variation that actually is explained by your group labels. And in fact, come to think of it, right? In fact, you may actually also look at the R square of ANOVA. you can actually similarly use the R square value of ANOVA to perform variable selection. Although I would say both of these things are more or less the same, right? Because your R square basically is related to your F statistic. Right? So later we will actually look at that. Okay. Okay. So those are the two common tests that you can use to. So okay, maybe I just write it out like this. X1, X2. Again, you have these variables. And this is your class label. Okay. So this will be maybe I have 0, 1, 2. Okay. And so on. Okay. Maybe just 2, right? Just 3 classes, right? So again, basically, if I have if the data is more or less the same for this column, then the ANOVA F statistic here will be close to 0. Right? So the F statistic is actually a positive value. The larger it is, if it is large, it tells you that the different groups, right? The variation between group is much stronger than the variation within group. So like in this case, if you have the values here are very high, this one very little, this one moderate, then this ANOVA will be high. Okay, because the within group variation here is actually small because all of them are more or less high. This one are also consistent. This one also more or less consistent. Some of them you may get something like this, like noisy. Generally it's large but it's noisy. So this one maybe also similar, noisy. Okay, this one is also noisy. So in this case, the ANOVA will also be low. All right. The ones that are very large ANOVAs will be again. Well, this will be very large if you have something that's very consistent. This one maybe. Okay. So this will be large, right? Because you see that the group difference, right, between them is large, and the variation within the group is actually very small, right? So that's the noise is small, but the signal is strong. Okay, so in this case, your F will be strong. So basically, again, it's the same idea. You have the variables here. This will be your F statistic. So you can plot them, and it may actually look something like this. There may be a jump. So I will basically just cut here. I'll take this group, right? I'll just take this group, which means I will eliminate this. I'll throw away this. Okay, and some other guys, right? And this one I'll take in, this one I'll take in. Okay? So this will help you work with a more compact set of data. Okay? Than the original data set. All right. It will at least help you focus more on the meaningful variables. All right. So we know how to deal with two types of. Sorry, we know how to deal with a case of numerical data. Well, how about categorical data? So we may have some data that's categorical, right? So for example, some basic ones may be smoking, non-smoking, smoking. So you may smoke, you may also not smoke. Okay. What else? Maybe drinking. May not smoke. Well, sorry, may not drink. Some people may drink. Okay. Maybe have a condition. Maybe have diabetes. Okay, and so on, right? So So these are yes, no, but you can also have more than that. Like for example, you may have, let me see, maybe eye disease. So you may have different codings for the eye disease. So 0 for no disease, 1 may be coding for something, maybe cataract. 2 is maybe dry eyes, and maybe 3 is some kind of conjunctivitis. Okay, so may have, you can have multiple levels. This one 2 levels. Okay, but this one can be more than 2 levels, right? So in this case, how do we do variable selection? Right. So again, the idea is to use a proper. So you have the label here, right? It's a class label. So the class label over here, I will just put 0. So in order to do variable selection for categorical variables, we will use the chi-square test. Actually, the chi-square test statistic. How many of you are not familiar with the chi-square test? Come across it before, at least heard about it or used it before? Jake has heard about it. Have you used it before? Okay, once or twice. All right. Others, how about others? Have used it, yeah. Learned it before, but I need some time to pick up. Okay. Actually, a lot of you may have learned all these tests in a way that is not very intuitive. So that's why you cannot remember it. There are certain ways to learn these things that if you learn it correctly, you will not it will stick with you for the rest of your life. Okay, so in fact, you can actually, yeah, it's actually you have to get the idea of the test. After if you can get to that, then it becomes very easy to discuss and relate. Otherwise, if it is just a formula for you, right, like a cookbook, it won't stick in your mind. So okay, so let us look at it now. So basically, our chi-square test is you are testing for association between you're testing association between 2 categorical variables. Okay. Now your label, right, is categorical because it's 0, 1. And all these are also categorical, right? So that's why you can use your chi-square test, okay? So the first thing that what it does is that, so you will, let's say you look at alcohol and label, right? So you will tabulate. So you basically have a table, right? This is what we call a contingency table. Two by two contingency table. 0, 1, let's say this part is for alcohol and this part is for label, right? Okay. So you have 0, 0 here, right? So it's 0, 0 here, so you have a count of 1. This is 1, 0. So alcohol 1, label 0, there's a count 1 here. So 0, 0, you have another count here, right? So you can keep counting and 1, 2, 3, 4, 5, like something like this. You can do some counting like this. For example, right? Okay, I just give some, this is basically just an example, right? So after you do the counting, then you can actually, you can count how many and then you can fill up the numbers, right? say maybe this is 5. Maybe this is 5, this is 10, and this is 1, and this is 2. Okay, or whatever, right? So once you have this table, right, then you can do a chi-square test statistic. So the chi-square test statistic, maybe just intuitively to give you an idea, if your two variables are associated, if associated, your chi-square test statistic will be high. If not associated, your chi-square test statistic will be low. In fact, will be close to 0. Okay, so generally, how do you see whether the pattern is without actually going to calculation? You can actually see whether there's association or not by checking the distribution of the count in the table. All right. If the data, if the values are distributed along the diagonal, let's say most of the data are distributed along the diagonal here, right? That means when you can see that when there's alcohol is 0, it is always very frequently sticking with the label, yeah? 15 of them. Or when alcohol is 1, the label is 1. So it's kind of like going together, you see. So in this case, there's actually, by just looking at it, you'll see that there's association. And whereas you look at so the other two are actually relatively weak compared to the pattern in the diagonal. Of course, you could have the pattern of the diagonal could go like over here. Okay, for example, this may be, it may be reversed, right? So maybe this may be small. This may be like maybe 2, this may be 2, this may be 15, and this may be 10. Okay, so it's reversed in this direction. This is also association, yeah, whereby when the alcohol is 0, the label is 1, and when the alcohol is 1, the label is 0. Okay, this is also an association in a different direction, right? If both things are not associated, they will be random. So if both things are not associated, then it doesn't matter, right? So the values will, all these values will get distributed around the cells. Maybe this is this will be 15, maybe this will be 12, this may be 12, this may be 11. So a pattern like this is actually almost whatever pattern that you see that's slightly more 15 here, they basically just by chance, right? So in order to formalize, so in this case, your chi-square will be actually quite low. Okay. In fact, if it's exactly the same, right, your chi-square will be equal to 0. Okay. It's totally uniform, right? So there's no association. Association means that the things are having some kind of bias, right? So like for example, if it is biased on the diagonal or biased to the off diagonal, right? But if there's no particular direction, then there's no association. Okay. So so basically, what happens is that you calculate the chi-square. You calculate the chi-square value for all these categorical values, right? So you may have maybe, let's say, this chi-square value may be high, this may be close to 0, this may be maybe just normal, and maybe this is also high, right? So what you will do at the end is you will eliminate this. Again, you will use the method of making a plot like this, right? This will be your variables, this will be your chi-square value, right? So again, you see that there's a jump, you cut and then you take, right? So maybe like this one you eliminate, right? So you keep these two variables. All right. So the idea is the same, right? Except that you're using a different test statistic. Okay.
Just wonder, right? Is it like association and correlation is similar, just that association is for categorical variable and correlation is for numerical variable?
Well, okay. It's the usage of the term, right? Usually association is kind of like a more general relationship. This correlation usually is reserved for linear relationship. So because when you are looking at categorical variables, right? There's there's nothing to talk about linearity, you see. So that's why we just say that we know that they are associated. So this implies a more general kind of relationship. Okay, there's a relationship, but it's we don't know whether it's linear or not. So we use the term association. In fact, so correlation is usually reserved for linear relationship. Because if you say that X is correlated with Y, basically you are saying something like this. You're saying that their relationship may be something like this, where you could actually this kind of like describe it with a linear model. Okay. If your relationship is not linear, right? If let's say you have something like this. So the relationship is kind of like quadratic, right? So this, again, we would say that X is associated. We will say that X is associated with Y. Okay? Perhaps we will say non-linearly. So association is just saying that there's a relationship, but it's a more general thing, whereas correlation usually implies the linearity.
Then is there any way to measure the association other than using the chi-square test, since I think chi-square test is for more to categorical variables?
Well, it depends on your data type, right? So this one is for your association can be for categorical.
Yes.
It can also be for numerical.
Numerical, yeah.
Like for example, if you do a scatter plot, you'll find that the pattern is like this. Then you would say that X is associated with Y. Maybe maybe you want to be more specific, like quadratically.
Quadratically, yes.
It will depend. Maybe sometimes the association it will go like this. Then you will say it's associated with X and Y are associated, maybe like periodically. Okay. Yet there are many more associations. Like sometimes the value may be like over here, then suddenly it will jump. This is also some kind of association, right? Goes like this, then it jumps.
Yes.
It's just that it's not your linear association.
Yeah. I mean, like there's no other test to test it, is it? Like, how do we test the association? Like something like Y squared to the X squared or X cubed periodically, or something like the one that have a jump.
So usually, if you are dealing with like just two variables, then the best way is to check the scatter plot. Yeah, that's why I don't encourage people to actually directly compute a correlation value, because without checking the scatter plot, because it can be misleading, you see. Like for example, this quadratic curve, if you calculate the correlation,
it can be zero. Yeah.
It can be zero, because your correlation is trying to fit a linear relationship. So the best fit will be actually a flat line like this.
Line. Yep.
Yeah. So in fact, over here, if you never check the plot, right, the computer software will tell you the correlation is some value close to zero, and then you would believe that, oh, X and Y not related.
Not related.
Which is wrong because it is related, but it's not linearly. Because you have to remember that the correlation calculation, right, assumes linearity, you see.
Yep.
So when that assumption is already off, right, whatever you calculated does not make sense. So this is one very common problem with people who work with data. They, especially it's still a problem like when they look at large amounts of data, they will, but sometimes you have to be, sometimes, right, when you're dealing with large numbers of data, right, it's not possible for you to check all the scatter plots.
Generate a scatter plot. Yes.
Yeah. So then they kind of like still make the calculate, because especially like let's say you got 100 of variables. How can you check all the pairwise?
How can you analyze the
It's
yes,
not possible
yes.
for you to check, you see. So yes, there's also a problem like how do you actually know whether the correlation value that you have computed without checking the scatter plot is real? The fact is you don't really know unless you check the scatter plot. But then there are too many of them to check, so what to do? Okay?
Yeah.
So this may be a very tricky problem, and I think the only way to manage it may be you reduce your data dimension to manageable scale, and then you only check at that level. There are different opinions about how to do this, but I think without reducing the dimension, you basically cannot manage to check all these things graphically. There are some people who try to develop a general kind of measure of association. There was a paper, there was I think maybe, I don't know, quite long already, maybe close to 10 years ago. Supposing that is created, this is actually a problem that has been around for a long time, okay? So somebody claimed to have invented a measure for, kind of like a measure to, that can tell you whether there's association or not. And the association can be non-linear, and it will pick up, right? But does not seem to have really taken off because it's actually quite complex to use. So yeah, we are still back at square one where we are still using some very crude way to measure association. At least in this case, always starting with the assumption of linearity, which forces you to just have access to the Pearson correlation. Okay, so yeah, it can be tricky when you are looking at large data sets and you are trying to look at correlation between variables. That can be tricky because the measure that is standard in use now assumes linearity. Okay, so you are not actually going to do well if the linearity assumption is not correct. Okay.
Okay. Yep, understood.
Okay, so I think yeah, close to 7:30 now. So we take a break now, all right, and come back at 8 o'clock, right? So after that, in that time, we will look at some demonstrations, right, on how to do feature selection, and I'll show an example where when you use the correct feature, you apply feature selection properly to the Wisconsin breast cancer data set, right? You can actually discover some very good variables for classifying the benign and malignant types of the cancer. Okay. All right. Okay. So I'll pause the recording now. All right, and I'll come back later. Yeah. Okay. Thank you. Okay, so I define these two things, right? Malignant is which of the diagnosis, right? The column for diagnosis is equal to M, right? The double equals is a logical checker, okay? So you can actually see what happens, right? Malignant, okay? These are the indices for samples that are malignant for the diagnosis, right? You can actually verify that. And benign is you can actually check. You can type benign. Basically, it is just the indices, right, for the samples where that particular class is true. Okay. So using which is very important, okay, because it allows you to identify the indices corresponding to certain samples, so that you can actually retrieve such type of data. Then you are going to do your t-test simultaneously for every column, right? You're not going to manually do it, right? The purpose of learning how to do R programming is in a few lines of code, you want it to completely iterate through a particular procedure that you want to repeatedly apply. So here we will use the function apply. So we apply is the looping function to apply for. You want to the apply function is actually a kind of a for loop to iterate through rows or columns of a data frame. All right. So we're going to use this, but we can't use the whole data set because we don't want to look through column 1, 2, and we don't want to look through column 1 and 2 because those are not. The first column is actually the metadata. The second column is.
Hi, Dr. Amy want to come in.
Oh, okay. Amy, let me see. Right. Okay. All right, so she's joining. Okay. Resume share. Okay. So we remove the first two columns, and we go by okay. Okay, so I'm going to show. All right. Can you see the output?
Yes.
Okay. So basically, maybe I just roughly explain what is going on here. So this apply, as I said, is a looping, right? So it takes in as input a data frame. So this is BC, right? Our object BC. Okay, this is BC, right? But we don't want the first two column, right? So we have minus, we kick away 1 and 2, okay? We can just represent it as 1 to 2, 1 colon 2. Then you see the 2 here, right? This 2 means we are going, we ask it to look through the columns, right? Because we are going by the columns, right? We're going to do the t-test based on each feature, isn't it? And then for each of the column, then we define a function, right, to do, right? So this function, then you see there's an index k here. This can be anything. You can use I, you can use j, whatever. But basically, this k here, right, is referring to each of the is a representation of the column of this data frame, right? So it will look through the first column, the second column, the third column, and so on, right? So basically, this k is the indexing the column, right? So we are trying to say that we do a t-test for that particular column So we'll split into two data sets. The first one is for this column corresponding to malignant samples, okay? And then the second one is benign samples, all right? So t-test will take in two data sets, right? Because we are doing a 2-sample t-test here. And then you have after that, you have a $sign statistic. This is to extract the t statistic out of t-test, because the t-test will give you a report that consists of multiple things. We don't want that, right? We only want to take out the statistic. So that's why you do that, you close it, and then therefore that's why you get this output. So it's very nice. In one line of code, you already got all the t statistics. Now, of course, actually it is better to store this as an object, right? So store it as t, right, so that you can actually use it later. Okay. So now after I have t, right, I can actually try to plot the diagram and see, right? Plot. I can plot t. I want to sort the t and then plot it. Okay. So let's try it. Okay. Let me show you. Can you see the scatter plot?
Yes.
Okay, so basically, this is just a rough plot to see the patterns of the t statistic, right? Here I didn't take the absolute, okay, although it is okay to take the absolute, so then you don't have negative values, right? Now you can see that most of the variables, so relatively you see that there are some that have very high t statistics value. Okay, especially I would say maybe looks like there's a cluster here, right? There might be a cluster of them here. So again, it depends on how much you want to shrink your feature space, right? If you want to shrink it to let's say 4, right? You look at this part here. So seems like you would take this top 4, right? Okay. If you want to expand it a bit more, you could take up until this part. Okay, because there seems to be a gap here. Okay. So this is how you actually look at it. If you are kind of very conservative, you only want to kick away very few things, then you might actually just kick away the tail here. Okay. But let's say we are kind of feeling a bit adventurous and we just want to really shrink the feature space a lot. So let's say we take the first 4 here. Okay. Let's look at this first 4. Right. We can actually sort t. We have a look.
So you disable the screen sharing.
I accidentally pressed something. Just a minute. So, okay, can you see? Can you see my console?
I can see something like untitled that I'm not so sure if it's your R console.
Share screen. Okay. Can you see now?
I can see your entire desktop. Yeah.
Okay. Can you see?
Yes.
Okay. So you can sort. So when you sort, it will sort from smallest to largest, right? But you can also ask it to sort from in a decreasing order. So you can put something like this: decreasing equals to true. Okay. So here you can see that the
the top four are what? Concave points, worst, perimeter worst, concave points mean, and then radius worst, right? So suppose these are the four that you want to take, right? These have the largest magnitude of the t statistic. Now, if you look at this carefully, you would see that concave points worst and concave point means you don't need to take both because they are just basically different aspects of the same feature. So you might actually just settle with concave points worst, and then you could take perimeter worst, and then you could take radius worst. All right. So you got these three variables. Okay. Now, so of course you could actually plot these three variables, right? You could keep these three variables. You can explore their pairwise scatter plots and all that. If you are going to be a bit more adventurous and maybe try to shrink everything to just one variable, what would you do? What would be the simplest thing to do? So we're going to use these three variables, right? Based on feature selection, so we maybe settle on these three. So let's say if you are going to reduce it further, like let's say perhaps just shrink it to one variable, how would you combine these three variables?
PCA? Or you mean like how do we plus minus operation create new features?
Of course, definitely you can do PCA here. But again, you see, because you're already three-dimension, right? So yeah,
yeah, there's no point. Yeah,
it may actually be able to shrink to one dimension, and that may be good. Of course, you can do. So we can actually look at that. Okay, so we try some standard methods first, lah. Let's say you do PCA, right? So using those three variables, right? So now I'm going to just extract these variables. So since we have just a few variables, I will just type in the variable names. Yeah. Okay, so I will do it like this. Okay. So that will be my BC select matrix. All right. So then I can do my PCA. So using the correlation matrix, right? And after that, look at the summary, okay? So, oops. Okay, so as expected, your first principal component already explains 91% of the total variation. The second one, so first two already almost explain everything, right? As expected, because you have already done feature selection, which already kind of like pick up the main signals, and then when you further compress, of course, you will get good compression like this, right? So let me see. So then after that, well, if you want to just do the PCA plots very easily, you can just do it like this.
use the pass function, yeah. So that will give me okay, can you see my plot?
Yes.
Okay, so basically basically the separation is on PC1 lah. Okay. PC1 there's some yeah, mainly on PC1, right? So let's check the loadings for PC1. Okay, so the loadings for PC1 will be so all three I have the same sign, right?
Yes.
And so basically those that are relatively large in perimeter words, relatively large in radius words, and relatively large in concave point words, they will get pushed to the relatively negative side. Okay. So basically this this has some direct interpretation, right? Okay, so but still you're using three variables, yeah. So so I can show you one way to think about it. So you could think about it like this. Why don't you multiply all the three variables together? If you multiply them together, you will produce just one variable, right? And perhaps this variable itself is enough to separate. Okay. So what we will do is I will do the following. Okay, I will okay, sorry, this should be a prompt. So I'm going to look through by, you see that I'm doing apply I'm doing apply BC select, right? So I'm going through the BC select here. Okay. You're just seeing the console, right? You're not seeing other things, yeah?
Yes.
Okay. Because I have a whole bunch of other stuff on my desktop now, so that might be too much for you. Okay. So you can see that I'm taking the product. I just take these three things, multiply together. Okay. So so I go by the row 1. That's why I have 1 here, and then I have PROD is product. Okay. So it just multiplies everything together. So then you can see that there's 1,000 something, 700 something, and all that. Okay. So after that, you can try to make a box plot. Okay. So how do I do that? You can have a box plot to kind of like visualize the data a bit. So I'm going to join two things together. I'm going to join the score with the class label together. Yeah. I'm creating a data frame with the score and the with its class label. Okay, it's just something like that, right? And this allows me to use the very simple way to visualize the box plots. Okay, then I will choose the color. So always the color is defined, the sequence of the color follows the sequence of your class label, right, in alphabetical order. So I will have benign first, benign I will put blue, and magenta for malignant, right? Easy to remember. Sometimes you forget which color is for which. Okay. All right. Okay, let me show you the
Can you see the box plot?
Yes.
Okay, so there's actually quite a large difference, right? Between it's actually quite a large difference between the two classes, and in fact you so basically you see that the benign for the benign samples, if you take if you measure all these three things, and you basically, in fact, you only need to measure two things. One is the radius, because the perimeter is actually, sorry, that's the perimeter, right? The perimeter is actually, I think it's using perimeter, right? Radius and perimeter, okay? So your radius times perimeter will basically give you some kind of area, all right? Because it will be r squared, okay? It's a function of r. So you multiply together, you get something like an r squared. And then concave points, doesn't matter. Maybe it will maybe for certain kinds of samples the concave points are more. I think clearly in this case, possibly your concave points for the malignant case is actually more. That's why when the three values they will multiply together, right? They become large. Okay, compared to the benign case. So over here, this looks very promising already, right? So in fact, when you later, let's say you want to do some kind of machine learning model to make predictions, you could actually just play with one variable, right? And that model will be very simple. So in this case, this is an example how you can start from I think the original data set has got like 30 variables. After you have done feature selection, with some careful considerations, you get 4 variables. You could proceed to do principal component as a standard, but then that will still leave you with 3 variables. Yeah. But again, since you from the principal component, you could also come to something like this, because your first principal component, right? Is basically your first principal component is basically you have the loadings there, and the loadings are more or less the same. All right, so you could actually create a variable. So you basically just create a variable by multiplying those 3 variables. By adding those 3 variables that are scaled with the loadings of the principal components. Okay, so that will also help you create another variable. Just the principal component and use it for machine learning purpose, right? So this is more like a kind of like an ad hoc method where you basically just multiply the 3 things together. Okay, so what I'm trying to show here is that there's actually a lot of ways things can be done here, right? So principal component is one way, but it's just going by linearity, right? And sometimes if you do it multiplicatively, right? You use a more multiplicative approach. You might actually get something that is better. Okay. So the idea here is that there are many possibilities towards the end, and you should not you should be kind of like brave enough to try some different approaches. Yeah. Okay. All right. Okay. Is that clear enough for you, everyone?
Yep.
Are there questions? Let me see. There's a question. All right. Okay. So later I will just share this as an example. Right. Now, if you want to, so the same, it's basically the same thing. So if you want to do chi-squared, so ANOVA is slightly more tricky because the output, right? Basically, you want to extract the F statistic output from the ANOVA table. So that one is a little bit That one I probably will have to give you some sample code, and then you can actually use that. Because otherwise you may not, unless you have some experience in R, otherwise it may not be clear to you how to extract the F statistic. Because in ANOVA, they output the ANOVA table. So basically your F statistics is kind of like hidden in one of the columns there. So you have to know how to get it out from the R output, okay? For chi-square statistic, let me see if there's a suitable. Okay, you could try something like this. Now, first I will just convert the, okay, so we have the iris data set, right? This is the iris data set. I could do something like this. I could actually convert the iris data set to a categorical data set, like as follows. So I'll remove the fifth column, go by.
So we are still at the graph.
Okay, I'll change it. Console. Okay. Can you see the console?
Yes.
Okay. So I'm going to convert the iris data set to a categorical data set, right? So first I check the summary statistics, and then I'm going to recode the data by, so if it's larger than the median, I will code it as 1. If it's smaller than the median, I will code it as 0, okay? So I will have iris. So I'm just going to manually do this. Iris2 is a clone of iris. Iris column 1. Sorry, iris2 column 1, right? More than 5.8. Iris maybe I found which of the iris column 1 is more than 5.8, and which of the iris column 1 is less than or equals to 5.8. Okay. Of course, I'm going to get a lot of things. So let me see. So I might actually I'm just going to do something like this. This will, I'll call it A1. I'll call it A2. Okay. So iris column, iris2, A1, column 1 will be 0, and iris 2, A2, column 1 will be. Actually, I think it's the other way around. So this will be 1, 2. Okay. Let's try. So let's look at my iris 2. Okay, so yeah, I changed it already. So, okay, I can actually tabulate iris column 1, iris 2 column 1. Table. Okay, so I got it, right? So about 80 of them are 0, 70 of them are 1. Okay, so I'm going to repeat this for the others. So I'm going to just change this one, just to be a bit patient. B1, B2, B1. This will be 3. Okay, and then I recycle the codes. So I basically change this to be
B. Right, okay. Then I change this to be C. Oh, I think I messed up. It should be, I should go to column 2 already. Right? Okay, never mind. I'm just going to redo this a bit. Iris2 equals to iris. And just do it again. CA1. And be careful here. I have to be okay. So this is column 2, yeah. And so I change this, okay. Right. And I change to column 3. Call this C1 and C2, yeah. And I have to change the value. So from median 3, I change to 4.35. Okay. So I change. Oh. Okay. Right. I am clumsy. Okay, let me do this on my notepad faster. And D1, D2. Okay, the last one, the median is 1.3. Okay, I think Jake, you have it right. Okay, good. Okay, right. So let me just run this. Error unexpected symbol. Okay, so 1, 2, 3. Oh, again. Run it again. Okay, finally. Okay, so I basically converted it into a categorical data set, right? This is just to illustrate to you how I'm going to do the feature selection using chi-square, right? So for that, I'm just going to recycle the code that I used for the earlier feature selection. Iris2. Okay. Can you see the code?
Yes.
So basically, it's still going by apply. So you give the data set with the categorical variables. That's iris 2, right? Without column 5. Column 5 is the because we're just going to look through the categorical values, right? So go by the column, right? So it's going to go by column. And then as usual, your function, you define the generic index there, k representing the column. So for the column, you're going to do the following. You do the chi-square test on the contingency table, right? So you can actually tabulate. R will create the contingency table for you. So you apply the chi-square test on the contingency table. And the contingency table is basically a table, the column with the class label, right? So very easy, chi-square test, and then you extract the test statistic, right? So in this case, you extracted out, you have turns out the petal length and the petal width are the ones that are the strongest for separation, okay? Sepal length and sepal width are actually not so important, less important, right? In fact, based on this result here, you could already say like, well, probably I will just look at, of course you can just basically, well, there's no point you do principal component if you only have 2 variables, right? You can, but a bit of an overkill lah. So if you just look at the plot, right, you can actually plot these 2 variables, petal length and petal width, right? So those are the 3rd and 4th columns, right? And you could just look at the distribution a bit. Go by, again, color is okay. Okay, so let me share the screen. Okay, can you see the plot?
Yes.
Yeah. Well, so basically, already petal length and petal width already settled the separation problem, right? You can see there's one cluster at the corner, one cluster in the middle, and there's one cluster here. There's actually some overlaps, yeah. So a lot of the data points, they have similar values, so they have the same position on the scatter plot. So if you want to see them, like there are several ways. One is you use transparency. The other is to jitter it slightly, okay? But anyway, those are just small things, yeah. So in fact, if you do principal component, right, basically you are sure to get just one variable, because you can see that there's a line that fits through this entire data here, right? And that can be your first principal component axis, right? And then after you make the rotation, basically one variable will be enough to distinguish between these 3 classes of flowers, okay? So, but this is mainly more as a demonstration for the application of the feature selection of categorical variables, okay? All right, is it clear for this example?
Yes.
Yes.
Okay, great. So for this remaining half an hour, I want to then talk about the assignment, yeah, the continuous assessment questions, because I have 4 data sets and I have assigned the students to work on the data sets separately. All right. So I'm just going to take you to Spectrum.
Okay, can you see the?
Yeah.
Okay, so this is the write up, right? So there are 4 data sets provided, and for the background, you can refer the attached links. So you should actually click these links to read more about the background. Okay. These are all 4 data sets that I have actually looked at, and I carefully chose them, right? And I think you can get meaningful results out by applying the things that you have learned up to today. Definitely you will be able to find something useful. In fact, you might find something that I never thought about. Okay, so it will be very interesting. So I would say you will apply suitable data processing and visualization methods up to this week. All right, you don't have to apply other things. Okay, I'll just assess up to whatever we have covered until this week. And the main idea is that we are able to discover meaningful patterns in the data and try to explain which variables actually are associated with those particular clusters, right? So for this, you only need to make an online presentation. Okay, 10 minutes for presentation and 5 minutes Q&A, right? So you don't need to write any report for me and whatever. So you can do your own things, and then finally come together as a group to make the slides and then do the presentation, right? To talk about how you approach the problem. Okay. So the assessment will be the following. So there are 20 marks there, right? So the methodology, the way you actually, what sort of methods you use, and all that, if you apply them appropriately, that counts towards methodology, okay? And how you interpret the results, right? Whether you know how to interpret the results that come out from some methods, right? So that will carry 6 marks. Then the quality of your slides, right? If the slides are professionally done, okay, you will maybe get something like 3. Q&A is basically later the 5 minutes, so I have some query. If you're able to address them more or less, okay, then yeah, you can get a 3. Provision of R codes with proper commenting. So this is your separate submission just to check that you have done proper coding, right? You have to comment on your codes. Okay. So submission of slides and R codes to Spectrum by this date on the day itself, lah. Okay. After you can actually submit the slides after the presentation, right? Just and every team will receive a final score, all right? And every team members will have the same score. Okay, so these are the allocations. There are 4 data sets. Now, diabetes data set is it is less complex, all right? But maybe it's more challenging in terms of there are many interesting things that you can do with this very simple data set. So because of its relative simplicity, I just put 2 people inside this for this data set, right? I think it's enough. 3 maybe too many people. Okay, but the rest of the data I think put 3 people. Okay, so there are 4 data sets here. So each data set will have 2 groups, yeah. So we can see the how different groups do things differently. Okay, and maybe some parts maybe they will converge to the same result, but some parts maybe they are looking at it from a different angle. Okay. So there's a first data set, it's called the glass data set. So we're going to look at the data sets one by one, right? So by doing so, everyone is exposed to different diversity of data sets. Some data sets they have missing values. All right, and
I will later or more or less have some discussion about how you're going to deal with those things. Okay, the glass data set. So two groups, Alex, Chao Hong, and C Kim Ting. Are you guys here?
Yes.
Yeah. Okay.
Yes.
So yeah. So you get to know each other. Okay.
Okay.
Then glass data set. B Wei, Sun Mengyuan, and Dan Qiuhua. Okay. Are you guys here? Okay, and Chao Ziyun and Suchi Aida, one group. Okay.
Okay.
Then Farhana and Ruby Devi. Farhana is here.
Yeah, I'm here.
Okay, so you with Ruby and hepatitis C data set. Xingman Kid, Nurul, Alia, and Yu Jing.
Yes.
Okay.
Yes. Yes.
Hepatitis C and also Chang Tian Yi, Wing Fong, and Wei Silu. Okay.
Yes.
Mice protein expression data set. Qi Wei Yao, Farah, and Dat Yao. Okay. And also Hing Chun, Hafiz, and Cha Chong. All right.
Okay.
Okay. So you get to know each other. So suggestion on how to carry out collaborative work. Just get to know each other. Maybe you'll just have an e-meeting to get to know each other and maybe talk about. Possibly, I think better everyone needs to look at the data set first to have some idea about what's going on, right? And then when you try to do things together, right, I can suggest to you to use a collaborative platform called Trello, which is like some kind of workspace where you can actually post things there so that your team members can actually comment on it or add something. So it's not like you, so that it's very convenient. So you don't need to go back and forth through email. Yeah. So that's a little bit. The reason why there's this kind of tools is because email is not exactly the best tool to do collaborative work, right? Especially you have 4 or 5 people, then it's a mess, right? Your email is so cluttered, you will lose yourself in the thread, okay? So you try that, okay? Of course, there are other possibilities, so feel free to use other platforms. I'm just suggesting this because I have used it before, and I think that it's quite user-friendly, so easy to set up and all that, okay? Right, so basically this is the information. Then maybe we go to the data sets, right? So the data sets, let me see. Okay, the class data set first. Can you see the data set?
No.
Share. Okay, can you see? No.
Yes.
Okay, so basically this data set is concerning forensic work of classification of glass. All right. Now, a glass is a kind of material that may have different kind of chemical composition, right? And also its physical property like the light refractive index and all that. Okay. There's an interest in, like, for example, in crime scene, right? If the police picks up some fragments of glass, right?
they can subject it to forensic testing, right? To try to see whether this glass is coming from what source, right? Is it from certain kind of type of glass or what? Okay. So in forensic work, so this will be the kind of data that they collect, right? It will be useful. Okay. So they have a benchmark data here. This is actually real data, yeah. So they have got type 1, type 2, and whatever. So what these types refer to, you have to check the documentation. Yeah, they actually say what type 1 means, type 2 means. Okay. Ri is a refractive index, right? The physical property, the optical property of the glass. And this Na, Mg, Ar, Si, K, Ca, Ba, Fe are chemical elements. All right. How much sodium, magnesium, aluminium, silicon? You see that is predominantly silicon. Is glass, right? Glass is made from sand, so sand is silicon. Potassium, calcium, and then they sometimes put some trace elements like barium and iron, right? Now this data is very is not the usual kind of data that you see, because this is a compositional data. They add to 1. Sorry, here they add to 100, more or less lah. These are percentages. So if you sum these columns, right, they will add to 100. I've already checked. They don't exactly add to 100 because there's rounding error. All right. So you see that it's already rounded. So some of them will be slightly more than 0.1. Some of them will be less a little bit and all that, right? They won't sum to exactly 100, but they will sum to something that's close to 100. Okay. So with this kind of data, right, you cannot directly apply principal component. You can try it and you are going to get weird results. The reason is because for compositional data, right, they are sitting in a different space and not in the usual Euclidean space. Principal component works best in the Euclidean space, right, where everything is just in a real line. Okay, so every dimension is a real line, right? But your compositional data has constraints. You see, they have to add up to 100, and therefore they cannot go. They have no liberty to go anywhere along the real line, right? So they have a weird space. They have a space that's actually not Euclidean. So when you apply principal component, right, it's going to give you very strange results, right? You can try that and have a look first, right, to see what I mean. So for this kind of data, right, you have to do something called centered log ratio transformation. All right, so I'm going to briefly talk about it. What is centered log ratio? Yeah. So, okay, suppose you have just now. Okay, I'll just briefly. Can you see my whiteboard?
Yes.
I'm just going to write something like this. Okay. Okay, just for simplicity, right? Let's say I've got these 3 components. Maybe one more. So let's say I've got I'll convert it to proportion. Yeah. So for the data that you have just now, right, you have to divide by the sum first, yeah, to turn it into a proportion. So this may be 0.7, this may be 0.2, 0.05, maybe 0.05. Okay, this is maybe sample 1. I'm going to have something like this. This may be 4. Now, for this, right, the centered log ratio transformation works like this. So you will take this value. So I will denote it as x. So this is 1. 1 represents the ID. Okay. Ij, right? J denotes the column variable. Okay. You will divide it with the geometric mean of the row. The geometric mean is as follows. You basically multiply everything together. 2, X3, and X4. Right? If you, in this case here, you have 4 items, right? 1, 2, 3, 4. So you basically just multiply these 4 guys together, and then you raise it to the power of 1/4. This is what we call a geometric mean. Right? And after you have done this, you'll take logarithm. This is your ln, the natural log, right? So this is the so-called center log ratio. Once you have done this, theory suggests that this transformation will bring, will basically map the values in this constraint space to a space that is approximately Euclidean, right? Therefore, when you apply your PCA on this transform space, the transform space, it will be much better, all right? So here, actually, basically, this one you can do some basic math. So basically, this is just log of that particular value. Subtract, this is a ratio, right? So subtract log of this product, right? And as a result, this is equal to this. So 1/4 sum of log j, right? J is from 1 to 4, okay? So very easily is that to do the center log ratio, you basically log this guy, okay? You will log this guy, and then you will subtract the sum of the log of, so basically you log every one of them, right? After that, to convert, you take this, the log form, you subtract the average of the log. That's all. Okay? Yeah, so this is actually quite easy to do. So for example, over here, after you do the log transformation, if center log transformation, it will be log 0.7 minus 1/4 log 0.7 plus log 0.2 plus log 0.05 plus log 0.05, okay? All right, so and you do for every one of them, right? Now, so what you should do is therefore you should actually write a function, write an R function that will actually perform this center log ratio transformation, right? For data processing, okay? It's actually easy to do if you have everything is that's non-zero. The problem comes when you have something like this, because one of the variables here has a 0 value. So you are going to get problem when you do the geometric mean, because as long as one of these guys is 0, then the whole thing becomes 0, right? So then it becomes undefined because you are dividing by 0, okay? So for this, you have to use some tricks. Okay, I'll teach you how to do this trick here. Okay, the trick is like this. Okay, so this is 0, right? You add a pseudo value to each variable, okay? So this pseudo value should be something that is relatively small compared to these values, right? So for example, you may add something like 0.001. Okay, 0.001. Just make sure that this pseudo value is some value that is relatively smaller than the smallest of the value, right? For example, 0.001 is actually, how do we put it? 1, 2. It's 100 times smaller than the smallest value, right? This should be okay, right? It's 100 times smaller than the smallest value, okay? So this should be fine. So this one also added 0.001. So end up, this actually becomes 0.501, 0.401, 0.101, and this becomes 0.001. And because this is non-zero, therefore, so once you have this, right, it is still not over yet because this doesn't sum to 1, right? Sum to what? It actually sums to 0.5, sums to 1.004, right? Okay? You added the 0.01 here, right? So what happens is that you should convert this to 0.501 divided by 1.004 to adjust it. All right? So you do so for this one as well. Okay? All right? So once you do this adjustment, it will sum to 1, right? Okay? Is it clear to you how to use this method?
Yep.
So you add the pseudo count, and then because you add the pseudo count, your total sum goes out of 1, right? Never mind, you normalize it by the new sum. You will get the total sum normalized back to 1. Okay, so this is a usual kind of tricks to apply in data analysis when adding the trick of adding pseudo values to break singular points like this. Yeah, it's a common technique used when you come across some kind of data where you need to take log. Yeah, this is quite commonly done. All right. So you should make this transformation first, then only you should go towards the go to do your principal component. Yeah. Okay. Now, please don't force yourself to do feature selection if there is no suitable context to do so, right? Although it is possible to do it, but if you feel like you don't need to do it, you don't do it, right? Don't just simply do it because you have learned it before. Okay, you have to decide whether it is a suitable thing to do for your current data set. All right. Okay, so this is the glass data set, right? Then I want to show you the diabetes data set. Okay, can you see the diabetes data set? Wait, where is it? Diabetes data set. Okay, can you see the diabetes data set?
Yes.
Okay, so this data set is basically data set of symptoms, yeah? And all these symptoms are yes, no, yes, no, yes, no only, all right? So they have patients who by age and gender and then the symptoms, right? You have to decide whether it is appropriate to include age and gender in your model, okay, or not. You have to think about it, yeah? Because they could basically act as just metadata, so may not be useful for to actually look at, or maybe you have a different opinion, right? So you will have to decide, right? But the other variables here, they are actually categorical, right? And you have the class label here, right? Positive means got diabetes, negative means no diabetes, right? Since these are all in characters, yes, no, you will first have to convert it to 0 and 1. Yes for 1, 0 for no lah. Okay, to be consistent. So you could either do this. The simplest way to do this, maybe for those of you, you may actually just do the replacement in Excel, right? Just replace the yes with 1 and no with 0. That's very easy. Or if you want, you can actually go to R and then just write a script to do the replacement. But I guess you might find that using the replace function in Excel will be much faster. Okay, in this case. Anyway, up to you to first convert that.
after you convert it, for this data set, there are a lot of interesting things you can do. Feature selection, definitely you can do, because there are quite a lot of features here. Looking at principal components and yeah, things like that. Okay. All right. So there are some very interesting things that this data set can do, although it looks like quite simple. Yes, no, only. Okay. So yeah. Okay. So this is the diabetes data set. You may actually need to look up what these things actually mean, like these terms, yeah, polydipsia, polyphagia, or alopecia, and all these things, yeah. So do some checking of this, what these terms actually mean, and see if you can discover which of these variables is strongly associated with having diabetes. Okay. If you let the doctor see, they will immediately see it, right? Because they have the domain knowledge. But let's see whether you can discover similar domain knowledge as a doctor without actually studying medicine, right? That's the fun part, okay? And you arrive at the same conclusion as a doctor. Okay, then we have the hepatitis C data set. So let's look at hepatitis C. Can you see my hepatitis C data set?
No.
No. Okay.
Oh yes. Is it? Yeah. Right now, yes.
Hepatitis. I'm not sure. Am I showing hepatitis, or do you see the blood donor?
Yes, I see the blood donor. Yes.
Oh, okay. The blood donor, yeah.
Yep.
See blood donor, and okay. So the classes are, there are blood donors, and there are people with fibrosis, cirrhosis, and suspect blood donor. Suspect blood donor are, I think, blood donors who they think might actually have some kind of liver problem, right? So they flag it as suspect blood donor, right? And of course, you have in this data set, you have some missing values here. Okay, quite a few running around here. Okay. Now there are several ways to deal with the missing value here for this data set. I think in since I never actually really quite talk about a formal way to deal with it, so perhaps in this particular example, the easiest way for you to deal with the missing value would be just to replace it with the
median or mid.
with the class. Well, replace it with the median of the particular class. Okay. Like for example, you don't replace it with the median of the column, yeah, because it contains a mixture of different classes, right? So if the NA is in the blood donor, you replace it with the median of the blood donor, right? If it's the missing value is in the cirrhosis, then you replace with the median of cirrhosis, right? That will serve as a first approximation to data processing, right? Although a more formal way, you can actually use a program, an R package called MICE, M-I-C-E, that actually does the imputation for you, right? But since we haven't, not sure if we're going to touch it, but you can actually use that program to fill in the missing values in this case, right? That program is based on regression methods, right? It uses a regression method to fill in the missing values, which will generally be more accurate, lah. Okay.
Okay.
Right. But of course, using median is not that bad, lah. At least it is. At least it is kind of like easy to do, right? Okay. So the challenge for this data set is you need to deal with the missing values first. After you have because if you don't deal with that, you try to run PCA R will complain. Yeah, they'll tell you that your matrix has got some problems because they can't. When R tries to find the covariance matrix with NA inside, it will stop. All right, it will give you an error. It will tell you to get rid of the missing values first. Right. So, but then if you remove those samples with missing values, then you're losing a lot of samples. So that's not a feasible way to approach the analysis, right? So you will do the imputation by median. And then the rest of these you can also discover, okay? So you also need to decide whether age and sex just serves as a metadata or they are useful to look at as well. So you have the same situation as in the diabetes data set, okay? So these are the variables. So actually, if you know this, if you do this project, then you will have some idea next time. You go do a blood test, you will get some health report, right? They have all these things there, the ALB, ALP, ALT, AST. Those people, then you can see from here, people with liver problems, right? Which one of these variables is elevated? Yeah, so it's pretty interesting. Okay. So then I'm going to talk about the last data set, the mice data set, right? The mice protein expression. Now this data set is, yes, it is the largest among these data sets, right? It has many columns and it also has missing values. Okay, missing values. Okay. Now, can you see my screen, the mouse data?
Yes.
Okay. So for this data set, right, you will need to collapse. Okay, so you see that for here, right, there's a mouse ID 309, then there's a underscore 1, 2, 3, 4 until 15. It turns out that for each of these mice, right, they actually repeatedly collected measurements from them, right? Repeatedly collected measurements from them up to 15 times. Okay, so you have some information about internal variability. Okay, the variation of these values within the mice, right? So that may be something useful to look at if you are interested to study the stability of certain variables, right? You want to see whether its variance is changing even within a particular animal. But for the purpose of maybe just studying differences, right? You should actually collapse them. Okay, you collapse them. That means you have to take you got to kind of like do some kind of averaging out of these values. Okay, so you pick a suitable measure of central tendency to represent these 15 values. You collapse them, and then you will get your data set, right? And then yeah, so it just looks big, but I guess it is just because there are repeated values being measured. So actually not that complicated, right? Because the variables are of the same type, yeah, the measurements. These are basically just genes, the gene expression values. So you might actually have to, like for example here, right? This is all missing. So for some unknown reason, these are all missing, right? Maybe, okay, not sure what went on, but you could actually impute them. You can use some simple imputation methods to do that. But you don't actually need to impute each value, because if you collapse them into one single row, then you just need to impute one value from here. And you can use, maybe perhaps use a simple method like taking the median of the same group to impute it, right? So, okay, so you have the class label here, right? There are actually, I think, I don't know, like 4 class labels. You have to check the documentation, right? So they have the class label here. Okay, it just looks big, but I think it's manageable for these 2 groups. Okay.
All right, and then of course after that you can do principal components, right? And perhaps this one is because these are all genes, right? So genes are like interacting with each other, right? So it might be useful to look at the patterns of interactions, which genes are interacting with each other. That means maybe possibly useful to look at patterns of correlations between these genes. And of course, definitely over here, since you got so many variables, right? Feature selection will definitely be something that is maybe definitely something that you should try. And since you got more than 2 class labels, you definitely will need to try the ANOVA F statistic. Yeah. Okay. So I hope for these 4 data sets, you will learn something from working on your own data set, and also you can see you are exposed to other types of data, and you can see how people approach the problem of doing that, right? Then it becomes like more interesting, right? Because you are rather than I just give one data set, everyone is working on it. It is so boring, right? And no novelty, you see. So with this, I think although some of the data sets they have varying degrees of complexity, but I think it's manageable. Yeah. Okay. All right, okay, so are there any questions regarding this continuous assessment?
No question at the moment.
Anyone has questions? No modeling is required. No, because we are just using up to, you see these data sets, if you want to do, right, you can go from beginning, go all the way until you get a machine learning model trained. Definitely doable, but I'm just using the data set to work on up to the point where we are learning all these techniques, right? Data processing, data exploration, feature selection, right? So it's enough that you can get to this point. Maybe later, if we have some interesting models, we can actually use some of these data sets as an example. So don't do modeling, yeah, because just use the, I think there's enough things to talk about already with the things that you have learned up to week 5. Enough things to talk about. Any questions from students, other students?
No, for now. I have to start to look at the data first.
Yeah, look at the data first. All right, okay, so seems like no questions for me. Okay, so in that case, we are just 9:30, so so that will be all for this week, yeah. So later I'll post up the resources for some R scripts that may be useful for you. Okay.
All right, okay, so I'm going to stop the recording now. Have you signed your attendance?
Haven't.
Haven't. Oh, okay, I set it until 9:30, so never mind. I think everyone is here. Okay, never mind. I'll just I'll add 30 minutes more to it so that you can go and sign. Okay.
Okay.
Okay. All right. So I'm going to stop recording now. So enjoy your holiday break.